Hey, previously we enforced the first two rules for validating transaction data. First, there should only be one minor reward per transaction block. Second, the transaction must have valid output amounts, and this applies to both reward transactions and regular transactions. Now we get to the third rule for validating transaction data. The input balances for the transaction should be valid according to the blockchain history. Otherwise, an attacker could pretend to have a much higher balance than they should for that transaction. Let's start by filling out the test case for this. So head to the blockchain/index.test.js file. And there should be a relevant test case where the transaction data has a malformed input. So this is relevant to them being a bad input balance. The idea with this test is that we want to create a transaction that can pass the valid transaction check, but its input amount will clearly be off. So first up, we're going to use the regular wallet instance, but we're going to set its balance to something huge like 9,000. So let's set it to 9,000. And again, the way we're going to get around all of the valid transaction data tests and methods is that we're going to construct an evil transaction method from the start by essentially running the same block of code for creating this transaction as we do in the regular transaction constructor. So as a pointer, we're going to look at the transaction.js file and see how a transaction is created. First up, it has an ID, so a generated UUID. Then it has an output map and an input, which are the crucial parts. The output map is created and is generated based off a recipient, an amount, and then of course the sender wallet to generate the transaction for. The key of this is that it designates an amount for the recipient and it makes sure that there is a remaining balance based off the sender wallet balance. And it uses that sender wallet balance freely. It doesn't do any validation here based off the sender wallet balance history. So that is the key to generating the output map, having these valid outputs. And then with the input, it calls this create input function. And the key is generating an object that has an amount, an address, and then a signature that uses the actual sign method attached to the sender wallet public key. So essentially, we're going to try to reconstruct a transaction that looks as close to this official transaction as we can, but we're going to do it inline within this index.test.js file. So we've already successfully modified the wallet balance. Now let's also create an evil output map for our transaction. So let's make a constant of evil output map. And then in this case, we're going to make sure that the amount designated to the wallet public key is still something valid. So for a recipient, and let's call this recipient foo recipient, and this is going to be a key in the map, so we don't need any quotes, but you can add them if you like. Let's give the foo recipient 100. And then we're going to make sure that the balance for the wallet public key is 9,000 minus 100. So even though the wallet balance is clearly off, since they shouldn't have received this much currency yet, we're going to make sure that the output map is still balanced when it comes to giving a remaining balance for the wallet public key, as well as giving some currency to the foo recipient. Cool. And now we can construct the evil transaction object itself. So let's make a constant of evil transaction. And this is going to consist of an input and an output map. Now the output map we already have, and that is the evil output map. And the input as well is going to be an object for now. Now this input should consist of a bunch of fake values. First up, the timestamp should be an arbitrarily dated, or rather generated date. So that's easy to fake. The amount should be that wallet balance. The address should be the wallet public key. And here comes the key for faking some data. We're going to even give it a valid signature by calling the wallet.sign method ourselves and then passing in the evil output map. So overall, this represents an evil transaction object that can be generated by any attacker in the system. And now as we call new chain.addBlock, we're going to pass in a data field that consists of an array of this evil transaction and the reward transaction. Cool. Now in this case, we're going to expect the function to be false. So go ahead and grab any valid transaction data line that expects the new chain to be false. Overall, expect blockchain.valid transaction data, passing in an object with the chain as the new chain.chain to be false. And when it comes to these false cases, we're also making sure that the error mock has been called. So add a line that expects the error mock to have been called. Okay, go ahead and save this, and once you have all the changes, head to the command line and then fire up the test command. Now as it goes, it's going to pick up the new test, and what you'll find is that even though there's this really evil transaction data in the new chain, the valid transaction data method still returns false, or rather true, rather than our expected value of false. So this is bad. It's making sure, or rather allowing, a transaction that is evil to get past the valid transaction data check. So clearly this is no good. Now our solution is going to be to make sure that every transaction input is based on the actual blockchain history. Luckily, we already have a calculate balance method in the wallet class, which allows us to look at a true balance for the wallet based on the history of the blockchain. So let's require the wallet class at the top of the file within our index.js method, so that way we can use it right here in our valid transaction data method. We're going to make a constant of wallet, and then this is the result of requiring the wallet directory / index.js file one directory back. All right, now that we have the wallet class, let's head down to our valid transaction data method. Now in the else case, we're running for regular transactions. And in this case, we want to keep track of a true balance. This will be the result of calling wallet.calculateBalance. And we're going to pass in the chain, but this has to be this.chain in order to make sure that we're validating against the currently accepted blockchain. It's absolutely essential that we do not pass in this chain that we're getting within the method itself, because that is something that the miner, or rather the attacker, can fake as well. Okay, the address for this is going to be the transaction.input.address, and thanks to calculate balance, we should now have a true balance for this transaction. Cool. And now if transaction.input.amount is not what we expect, so if it's not equal to the true balance, then we should definitely return false from this method. This means an attacker is trying to fake their balance. And we're going to add a console.error and say that this is an invalid input amount. All right. With the save of this, check back in the command line. And I do have a typo, but as long as everything is spelled correctly and the test command actually reruns, what we should find is now a fully green passing test suite, since indeed blockchain/index.test.js is green. Cool. So now we're making sure that every transaction input amount actually matches the true balance in the blockchain history. Even when an evil transaction is attempted to be submitted, we're going to make sure that it doesn't pass the valid transaction data method unless its input balance actually is matching what we have in our blockchain. Cool. So there's one final rule to enforce. One of the simplest ways to get around having valid transaction data is to include the identical transaction multiple times in the same block. So let's protect the blockchain from this final attack scenario next.